Math 1343, Week 8, Video 13, a complete example of a test for association. This will be let's try that again. This will be the final video in this series. And even though we've used multiple videos, some of which went longer than others, to develop the technique for a test for association, it's actually not that bad, and it doesn't take that much time once you got your plan down. So let's jump right into it. The zoologist is concerned that different tracking devices affect penguin survival rates. Over a 10-year period, 12 of 50 metal-tagged penguins survived, while 15 of 50 electronic-tagged penguins survived. Test at alpha equals 10% if the type of tag affects survival rates. Use both the critical value and p-value approach. We'll do the critical value approach first, and then we'll modify it for the p-value approach. So, I invite you to pause the video and see if you can play out all 5 steps using the critical value approach and the p-value approach, and then resume the video and compare your results to what's about to happen. Here we go. For the critical value approach or the p-value approach, our first step, of course, is to state the hypotheses. But this is very predictable. For a test for association, the null hypothesis is always there is not an association. There is not an association between whatever two categories we're comparing, two variables we're comparing, between tag type of tag, and survival rate. Actually, that's not wrong. It's not wrong. But I'm going to reword it in the context of what we're being asked to test. We're being asked to test if the type of tag affects the survival rates. So let's think about this for a second. If there is not an association between the two, should the type of tag affect the survival rate? And the answer is no. So even though we had a perfectly good null hypothesis, I think I'd like to word it in the same phrasing as the question. In this case, the type of tag does not affect survival rates. So guess what the alternative hypothesis would be? The type of tag affects survival rates. Now, the other version of the hypotheses are perfectly correct. There is not an association between type of tag and survival rate. There is an association between type of tag and survival rate. But it's important to know that those can be phrased using different words, such as the type of tag does not affect survival rates, as opposed to it does. All right, so step 1, state the hypotheses. For the critical value approach, step 2 is to determine the critical value and regions. Critical value and regions. For the critical value, we would need to, well, first off, let's go ahead and sketch the chi-squared curve. Always a right tail test. Significance level is 10%, which means this area is 10%. We're going to look up our chi-squared in our chi-squared table, but we're missing something important. What are we missing? Degrees of freedom. The formula for degrees of freedom is still the product of, it's gone. The formula for degrees of freedom is number of rows minus 1 times number of columns minus 1. One problem, we have no contingency table. So in order to do this, we should probably have a contingency table. Plus, we're going to need a contingency table when we calculate the expected value. So at the beginning, if you were wondering, where's the contingency table? I didn't give it to you on purpose, but I gave you enough information to build one. How do you build a contingency table from scratch? Well, first, you look for the ways that you're segregating your data 2 different ways. In this case, we're segregating our penguin data by whether or not they survived and what type of tag they were wearing. So we can create an observed value contingency table pretty straightforward. Based on whether or not they survived or didn't. So we'll say survived and didn't. And based on whether or not their tag was metal or electronic. So let's see if we can process our numbers into here. Over a 10-year period, 12 of 50 metal tagged penguins survived. I got 2 numbers I can use. The second, 50, is the total number of metal tagged penguins. I should remind you that there is a total column and a total row. So if we say that there are 50 metal tagged penguins, where would the 50 go? Well, the 50 is the total number of metal tagged penguins, so it would go here. And we're told of those 50, 12 survived. So right away I can calculate this number, because out of the 50 metal tagged penguins, if 12 survived, then the difference did not. 50 minus 12 is 38. Now for the other numbers, 15 out of 50 electronic tagged penguins survived. That means there's a total of 50 electronic tagged penguins, so 50 goes here as well. And we're told that 15 of them survived, which means the remaining 35 did not. Knowing that we'll need all the totals, let's add up all the columns. 12 plus 15 is 27, so 27 of these penguins survived. 38 plus 35 is 73, so 73 of these penguins did not, out of a total of 50 plus 50, which equals 100. So now we know how to calculate our degrees of freedom. And one thing I needed to mention from the previous videos that I don't think I did, when you're calculating the degrees of freedom using the formula row minus 1 times column minus 1, these do not include the total row and total column. This contingency table has 2 rows and 2 columns. Therefore, the degrees of freedom are 2 minus 1 times 2 minus 1, but that's just 1 times 1, which is 1. So we hit bare minimum number of degrees of freedom, only 1 degree of freedom. All right, so now we can use our chi-square table. With 1 degree of freedom and a right tail of 10%, our critical value is 2.706. 2.706. Meaning that our non-rejection region is to the left of that, and our rejection region is to the right. I think the hardest part about this problem is creating this contingency table. All right, step 3. We calculate the test statistic. Recall that the formula for the test statistic is chi-squared is equal to the sum of the observed value minus the expected value, that's difference squared, compared to the expected value. So we have to calculate that for each cell, but we don't have our expected values yet. Let's make our expected value table over here, and remember how that goes. You set up the same rows and columns. We'll put S for survived and D for didn't, M for metal, E for electronic, but you import the totals over here. So we still need 27 who survived, 73 who did not, 50 total metal tagged, 50 total electronic tagged, 100 grand total. And then for each cell in the expected value contingency table, you calculate the expected value by multiplying the row total times the column total divided by the grand total. So, for the first cell, we multiply 50 times 27 and then divide that by 100. I actually don't need a calculator for that. 50 times 27 divided by 100 is 13.5. How did I do that? Because I switched up the order. I said 50 divided by 100, which is a half, times 27, which is half of 27 is 13.5. For the next cell, it would be 50 times 73 divided by 100, but let's do 50 divided by 100, which is a half, times 73. Half of 73 is 36.5, exactly. And we could calculate the rest of them, but I want to remind you that in the expected value contingency table, the sums are preserved. If you check the sum of these two, it's still 50. But the column sums should be preserved as well. So this number should add with 13.5 to give 27, and it ends up being 13.5. And this number should add to 36.5 to give 73, and it's 36.5. But it should also make sense that they match, because when I'm doing row times column, my row is the same, and so each column should produce the same value as the cell above it. All right, so there's our expected values, but we're not out of the woods yet, because we have to do this setup, this formula, to calculate the test statistic. We only have 4 cells, so it's not going to be too cumbersome. Our test statistic will be chi-squared equals. All right, let's start with the upper left cell, survived metal. What we observed was 12. What we expect is 13.5. That will get squared and compared to what we observed, 13.5. Plus, next cell didn't survive metal tag. What we observed was 38. What we expected was 36.5. That difference is squared and gets compared to what we observed, 36.5. Plus, I always do this. Run out of room. Next cell. What we observed was 15. What we expected was 13.5. So 15 minus 13.5 squared compared to what we observed, 13.5, plus, and I always draw it with this goofy pencil sharpeners. In the last cell, we observed 35, but we expected 36.5. So 35 minus 36.5 squared divided by what we observed, which was 36.5. I'm going to do the same thing that I did before, where I calculate the numerators separately, because I know what every one of these numerators are equal, and it wouldn't be that hard to see that. If you'll notice, every one of these differences is either 1.5 or negative 1.5. You can check. Negative 1.5, positive 1.5, positive 1.5, negative 1.5. And so when I square them, I'll get the same results. 1.5 squared is 2.25. So 2.25 divided by 13.5 plus 2.25 divided by 36.5 plus 2.25 divided by 13.5 plus 2.25 divided by 36.5. But, you know, honestly, you should just do the math in the calculator. But I always look for places to flex my brain a little bit more, because like any muscle, the more you flex it, the stronger it gets. All right, so let's put all this into a calculator. You could type it in straight from left to right, but I'm pulling a couple of tricks here to minimize the number of keystrokes. All right, I got to 4 decimal places a test statistic of 0.4566, but I'm going to put the problem in as is to make sure that in an effort to streamline the process, I didn't sacrifice accuracy. You know, faster is no good if the answer is wrong. So I want to make sure I didn't make a mistake here. Yep, everything's good. All right, so there's our test statistic. And again, this is the slowest part of the test word association because you have to calculate all your expected values and then you have to calculate the test statistic afterwards. But our test statistic ends up being chi-squared is equal to 0.4566. That's a really small test statistic. I'm not expecting to reject the null hypothesis. All right, so finishing the critical value approach. Now that we have our test statistic, our fourth move is to make a decision. And in the critical value approach, the decision is made by comparing the test statistic to our critical value. Our test statistic isn't even 1, so it barely gets past 0 over here and clearly lands in the non-rejection region because our test statistic is less than our critical value. So our decision, do not reject the null hypothesis. Since we're in the non-rejection region, do not reject the null hypothesis. And let's just go ahead and answer the question or draw a conclusion. I think I'll show now the 3-dot triangle. It's a symbol for the word therefore. Therefore, if we don't reject the null hypothesis, we conclude that type of tag does not affect survival rate. Type of tag does not affect survival rate because there's not an association between the two. Your tag has nothing to do with whether or not you survive, penguin. All right, let's quickly hit up the p-value approach so we can wrap up this video in this series. If we were doing the p-value approach, then we would not have done this. We would have done the test statistic, that would have been step 2, and we would not have made a decision yet. Our third step would have been to calculate the p-value. And remember, the p-value is the area of the tail cut off by the test statistic. It's still important to remember that it's a right tail test because we're going to draw a right tail, cut it off, and where's my marker? Here it is. And use our test statistic to cut that off. Chi-squared is equal to 2.706. The p-value would be the area here. And I'm going to do something that I don't really like doing. I'm going to move my phone so that we can see the chi-squared table. Of course, my computer just went to sleep, so I got to log back into that real quick because I did not draw the chi-squared row up there so that we can, password is incorrect, of course. 1 second, folks. Appreciate your patience. There we go. All right, so let's download this so it's in its own tab, and let's zoom in on it. All right, I'm about to grab the camera and move it around, so I'll have to fiddle with the focus. Oh, this video has been going on a long time. Good thing it's the last one. Okay, so let's remember what we're trying to do. We're trying to find the area or a range of areas for this. Oh, and our degrees of freedom is still 1. That's probably worth writing. For the same reason as before, because it's the calculation's still over there. You can see my stuff over there. All right, so we're at 1 degree of freedom, so we're in the top row, and we're looking for a chi-squared value of, what was our test statistic? 0.4566. So where is 0.4566? Well, it is between this number and that number. And since our test statistic is between these two numbers, we know that our p-value is between these two numbers. So our p-value is between 10% and 90%. Hello, person who opened the door. All right, therefore the p-value, sorry, let's do this. Therefore the p-value, we know it's greater than 10%, but it's less than 90%. And now I'm gonna put the camera back up here so that we can wrap up this video properly. Okay, that'll do. All right, so our p-value is between 10% and 90%, but more importantly, it's greater than 10%. And because the p-value is big, we do not reject, this would be step 4, do not reject the null hypothesis. and we draw the same conclusion as before, that the type of tag doesn't affect survival rate. You only have to do one type of hypothesis test. You don't have to do both the critical value and the p-value approach at the same time. It all depends upon what your professor prefers. And in my class, my preference is the critical value approach until we can't use it. And we will reach a point where we can't.